Hey everyone, and welcome back to The Explainer. Today we are unpacking a truly fascinating journey, the incredible life cycle of a sound wave. From the exact moment it's born, to the precise second it hits your ear, the physics happening right under our noses every single day are just amazing to think about.
But before we get into the nuts and bolts of how all this works, I want you to picture something. If two astronauts are working outside their space station and they clank two heavy pieces of metal together in the vacuum of space, does it actually make a sound?
You're out there in the total, absolute silence of the cosmic void. Now, down here on Earth, we intuitively know exactly what clanking metal sounds like, right? But what happens when you strip away our entire atmosphere? Keep that scenario tucked in the back of your mind as we go through this.
So here is our roadmap for today's explainer. 1. How sound is born. 2. Traveling through the void. 3. The shape of sound. And 4. Visualizing invisible energy. All right, let's dive right in.
Section 1. How sound is born. The power of physical movement.
Okay, the foundational concept we really have to grasp first is vibration. A vibration is simply the periodic to and fro motion, or oscillation, of an object. Pulling a stretched string, striking a metal plate, blowing air through a flute, all of these create rapid vibrations. Actually, try this right now. Go ahead and gently put your fingers on your throat. Take a deep breath and just hum for a second. You can literally feel the rapid vibrations happening right there under your fingertips.
What you just felt are your vocal cords, tightly stretched, muscular flaps inside your larynx. They are rapidly snapping open and closed to create speech. The air from your lungs pushes up through them, and that creates the physical disturbance that eventually becomes your voice. It all starts with that physical movement.
And you know, human culture has adapted to the production of sound in some pretty incredible ways. Take Kongthong, a village near Shillong in Meghalaya. It's actually known as the Whistling Village, and for a good reason. Everyone there receives a unique musical tune for a name at birth. A mother composes this beautiful, lullaby-like tune for her child, and that tune basically becomes their identity for life. It's just a brilliant example of how fundamental creating and manipulating vibrations is to the human experience.
Moving on to Section 2, Traveling Through the Void. Why sound needs a path.
So, we have a vibration, but how does it actually get from point A to point B? Well, the answer is a medium. A medium is the material, whether that's a solid, a liquid, or a gas like the air we breathe, that sound propagates through. Without this vital medium, the vibration is completely trapped at its source. It has nowhere to go. Sound literally uses the matter around it as a bridge to travel. Which brings us perfectly back to our astronauts. Scientists actually prove this absolute need for a medium using a vacuum bell jar. If you put an electric bell inside a sealed glass jar and turn it on, you hear it perfectly fine. But if you hook up a vacuum pump and suck all the air out of that jar, the sound fades away to nothing. You can look right through the glass, you can physically see the little hammer striking the bell wildly, but it rings in total silence. So those astronauts clanking metal in space, absolutely silent. Space is a near vacuum, so there's no air, no medium for the sound to travel through.
Section 3. The shape of sound. Compressions and rarefactions. Okay, so if sound pushes through a medium like air, what does that actually look like on a microscopic level? To picture this, think of a classic slinky toy. If you stretch one out on the floor and give one end a quick, sharp push forward, you'll see a distinct pulse travel all the way down to the other side. But look closely at what's happening. The individual coils of the slinky aren't sliding across the room. They just bump into their neighbor and bounce right back. The energy pushes through the coils, but the coils themselves stay relatively put. Well, air particles act the exact same way when a sound wave hits them.
When a vibrating object pushes forward, it squishes the nearby air particles together. This creates a region of higher density that we call a compression. Then, when the vibrating object pulls back, it creates a region of lower density, where the particles spread out, and that's called a rarefaction. So, a sound wave is essentially just an alternating, rapid-fire pattern of these squished and stretched out areas of air rushing outward from the source.
The crucial point to remember here is that sound is a longitudinal wave. That's a fancy way of saying the particles of the medium vibrate back and forth parallel to the direction the wave is traveling. It pushes and pulls in a straight line. This is totally different from, say, dropping a stone in a pond, where the water ripples up and down while the wave moves forward. Sound pushes straight ahead. Now, what happens if you push this to the absolute extreme? Think about a supersonic aircraft. If a jet flies faster than the speed of sound itself, it physically outpaces its own sound waves.
It compresses the air in front of it so violently and so rapidly that it creates this massive, sudden disturbance in air density. And when that huge shift in density finally reaches your ears down on the ground, you perceive it as an explosive, incredibly loud pulse, a sonic boom.
Which brings us to our final part today, Section 4, Visualizing Invisible Energy, Translating Movement to Graphs. First, I really want to loudly underline a core takeaway from our source material here. In the propagation of a sound wave, it is the energy that is transferred, not the particles of the medium. If you remember one thing today, make it this. The air sitting right next to a giant speaker at a rock concert doesn't travel across the room and into your ear. That air stays right by the speaker. Only the invisible, propagating energy travels to you, bouncing from particle to particle like a relay race.
So how do scientists actually draw and measure this invisible energy? Well, they graph the density of the air over distance or time. Whenever there is a compression, that high-density squished zone we just talked about, it's drawn as a peak on the graph, which is called a crest. And whenever there is a rarefaction, the low-density stretched-out zone, the graph dips down into what is called a trough. This takes all that chaotic and visible bumping of air molecules and neatly translates it into these smooth, wavy lines that we all recognize as sound waves.
Which leaves us with kind of a mind-bending thought to close out on. If every word you hear, every song you love, and every rustling leaf is just a wave of invisible energy physically rippling through the matter of the universe to reach you, what other invisible waves do you think are passing right through you at this very moment? Thank you so much for exploring with us today. Keep your curiosity tuned, and we'll see you in the next explainer.